Hello everyone and welcome to the coronavirus edition of the 8th lecture from our signal theory class. In this lecture we will briefly go over how we can solve differential equations using the Fourier transform, and then we will move to the Laplace transform. In the previous lectures, you have seen that the Fourier transform can be used not only for spectral analysis, but we can also use it to perform filtering in the spectral domain. We did filtering in the spectral domain with discrete time signals and systems. Now we have continuous time systems, but we can actually perform something similar. Moreover, this something similar is actually equivalent to solving the differential equation of a system. So, how do we use the Fourier transform to solve differential equations? This is our ordinary differential equation with constant coefficients, and to solve it with the Fourier transform, we need to examine three additional properties of the Fourier transform. First, we need to examine what the Fourier transform does with a linear combination of signals. When you apply the Fourier transform to a linear combination of two signals, and you crunch, you will get that it is the same linear combination of the Fourier transforms of those signals. So when you see a linear combination like this, you can apply the Fourier transform directly to these signals. Second, we need to examine for what signals the Fourier transform exists. For this purpose, the definition integral can be maximized by taking the absolute value of this argument. If this integral exists, it will always be greater or equal to this one. And because the absolute value of this complex exponential is always 1, this integral is always equal to this one. If this integral exists, and it is finite, it is actually a sufficient condition for the existence of the Fourier transform. Moreover, if this integral exists and it is finite, that also means that this function must have zero limit for time going to plus minus infinity. If this limit was not zero, this integral would not converge. So the Fourier transform exists mostly for signals that start and finish at zero. You may recall though that we worked with the Fourier transform of signals that do not satisfy this condition. For example, we worked with the Fourier transform of a sine or a cosine. But with these functions, I was actually cheating a little bit. To express the Fourier transform of a cosine, we had to use Dirac delta pulses, which are actually not functions. They are so-called generalized functions or distributions. And you may also recall that I have never actually evaluated this integral for sine or a cosine. I avoided that because this integral would not converge for sine or cosine. To show you what the Fourier transform of a cosine is, I gave you a spectrum with two Dirac delta pulses, and then I only computed the inverse Fourier transform to show you that it actually is a spectrum of a cosine. So, if you really want this integral to converge, you need this argument to go to zero for time going to plus or minus infinity. The third thing we need to examine is the Fourier transform of the derivative of a function. To do this, we need to use the definition integral and then evaluate it per parts. In the integration per parts, I will integrate this derivative of function f and differentiate this exponential. So first I will integrate this derivative of f of t, which will give me f of t without derivative. And I will just copy the exponential. And this I need to evaluate at these limits. Then I write this integral where I copy this function and take derivative of the exponential. That will give me this integral. Now I will use the fact that for the Fourier transform of this function f of t to exist, I need this function to have zero limits for time going to plus minus infinity. With this property, the value of this expression for time going to plus or minus infinity must be zero, so this will just give me zero. Now, this integral I can rewrite like this. And here I can notice that this remaining integral is only the Fourier transform of the function f of t without derivative. So I can write this. The moral of the story is that the Fourier transform of the derivative of a function is the Fourier transform of this function without derivative multiplied by j omega. So the Fourier transform has this magical power to turn derivative into multiplication. The Fourier transform can actually help us to get rid of a derivative and turn it into a simple multiplication. Actually, you can do this derivation for higher derivatives, in which case you will get that the Fourier transform of the nth derivative of a function is the Fourier transform of that function without derivative, but multiplied by the j omega n times. Each derivative gives you one multiplication by j omega. Now, using these properties of the Fourier transform, we can apply the Fourier transform to our differential equation. That means that I will compute the Fourier transform of the left-hand side and the right-hand side of this differential equation. On both left and right-hand sides, I have linear combinations of functions, so I need to apply the Fourier transform only to this y and its derivative and to this x and its derivatives. And when I apply the Fourier transform to the nth derivative of a function, I will get the Fourier transform of the function without derivative, but multiplied by j omega n times. This is what I get. The Fourier transform of y of t will be the uppercase y of omega. The Fourier transform of the first derivative of y of t will be the uppercase y omega multiplied by j omega. And the Fourier transform of the second derivative of y of t will be the uppercase y of omega multiplied by j omega squared. The same goes for the right-hand side. And here you can see that the Fourier transform turned the differential equation with derivatives into an algebraic equation without derivatives. So I no longer need to solve the differential equation, I only need to solve a much simpler algebraic equation. This is what I can do. On the left-hand side, I can extract y of omega, and on the right-hand side, I can extract x of omega. Now I can divide by this polynomial, and I get this. This expression says that the spectrum of the output signal will be the spectrum of the input signal multiplied by this function. And by now, I hope you all remember what is the name of the function that we need to multiply the input spectrum with to get the output spectrum. This function we call the frequency characteristic, and we denote it as uppercase h of omega. So basically the Fourier transform turns solving this differential equation into what you have already learned as the filtering in the spectral domain. Instead of constructing the characteristic equation, finding its roots and constructing the solutions, I can take my input signal, compute its Fourier transform, that is its spectrum, then multiply it with the frequency characteristic of the system, which will give me the spectrum of the output signal. Then I just need to take the inverse Fourier transform of this spectrum, and that will give me my output signal in the time domain. And how do you get the frequency characteristic? This is how you get the frequency characteristic. You can either do the entire derivation, or you can just remember this form and substitute the coefficients of the differential equation. This principle is quite neat. It allows us to avoid dealing with any derivatives, and we would start using it were it not for one problem, which is a rather limited usability of the Fourier transform. The definition integral of the Fourier transform converges for the absolutely integrable functions, and if you try to evaluate the definition integral for such basic functions like sine or cosine, you would find that the integral does not even converge. We can do some tricks with Dirac delta functions, but this has limited usability and it will not get you a spectrum of a real exponential or a polynomial. So overall, we like this idea that turns the differential equation into an algebraic equation and filtering in the spectral domain, but we would need to improve the Fourier transform so that it would have no problem converging for basic signals like sine, cosine, or exponentials. How do we do that? This is how we do that. We need to create a new transform that will keep the important properties of the Fourier transform, but it will have no problem converging with functions like sine, cosine, or an exponential. To create this new transform, we will start with the definition of the continuous time Fourier transform and introduce some minimal changes that will not screw up its properties but improve its convergence. The first change I will do is that in this exponential, instead of this purely imaginary j omega, I will use a general complex number sigma plus j omega. I will denote this number as s, which will turn my definition formula into this. This change is actually small enough to keep that nice property of the Fourier transform that turns derivative into multiplication. I showed it here. If you apply this formula to a derivative of a function and you use the same per parts integration as we did with the Fourier transform, you will still get that derivative will go away and you will get just a multiplication by s instead. Okay, so I still have that nice property, but what do I gain by this change? Let's examine that. When you write this s as sigma plus j omega and break this exponential into 2, you will get pretty much the same what we had for the Fourier transform, except now my function x is being multiplied by this exponential, which at least for positive sigma and positive time will exponentially approach 0. So even if the signal x does not approach 0 for positive infinity, there is much better chance that the product of x and this exponential will. Essentially, this signal x is now being exponentially damped by this exponential, and that can help with the convergence of this integral. But this holds only for a positive sigma and positive time. What about negative time? Well, here we have to compromise. We will say that our signals are not switched on from the time minus infinity, but we will assume that everything is switched on at time 0. Before time 0, all the signals or functions are 0. Mathematically, we can write this by multiplying our signal by a unit step. This will force our signal to 0 for negative time. When I do this, I do not have to integrate from minus infinity, I can start integrating from 0, and when I integrate from 0, I do not have to write this unit step here anymore. So when I do this, I do not have to worry what this exponential will do for negative time. I can just use its damping properties for positive time. So now, instead of this definition integral of the Fourier transform, I will use this definition integral, which we call the Laplace transform of signal x of t. And this Laplace transform will allow me to work with differential equations in a manner similar to how I did it with the Fourier transform. I will again turn a differential equation into an algebraic equation, and I will get that equivalent of the filtering in the spectral domain, except this time you will see that the Laplace transform converges for a wider class of useful functions. One detail to note here is that we actually integrate from left side of 0. That means that if, for example, a Dirac delta function is sitting at 0, it will be included into this integration. Now, similarly to the Fourier transform, we will denote the Laplace transform of our signal x by the capital X, except now we will call it the Laplace image of our signal. It will be the function of s, which we will call the complex frequency, and instead of frequency domain or spectral domain, we will have so-called Laplace domain. Before we move on, in this plot I illustrate what these changes do with our function. If our function x of t was a sine, when we introduce these changes, we exponentially damp the sign and we cut it off for negative time. So while this integral would not converge for this green line, when I replace it with this black function, this integral will have no problem converging, and in a minute I will show you that we can readily compute the Laplace transform of a sine or a cosine. Before we apply the Laplace transform to our differential equation, we need to take a look at some properties of the Laplace transform. This is actually pretty boring and rather long, but we have to get through it. First, the connection of the Laplace transform with the Fourier transform. I will assume that my signal is 0 for negative time, which is quite typical for impulse responses. Now, if you substitute j omega for s, you will get this, which you can express using the definition integral of the Laplace transform as this. Here, because this signal x is 0 for negative time, you can change this lower integration limit to -infinity, which will give you this. And this expression is actually the Fourier transform of your signal. So if your signal is 0 for negative time and you substitute j omega for s, you will turn the Laplace image of your signal into the Fourier spectrum of your signal. Next property, the Laplace transform of the Dirac delta function. Here I just need to substitute into the definition integral and use the sampling property of the Dirac delta function. That will give me this, which is equal to 1. So the Laplace transform of the Dirac delta function is 1. Next, the Laplace transform of a unit step. Again, I substitute into the definition of the Laplace transform and evaluate the integral. Here, if the real part of s is positive, the limit of this expression for t going to +infinity is 0. And the value of this expression at 0 is 1 over minus s. That will give me this result. So the Laplace transform of the unit step is 1 over s, and the integral will converge for real part of s greater than 0. Next, the Laplace transform of t. I substitute into the definition integral and evaluate it per parts. I need to differentiate t and integrate the exponential. This is what I get. Here, if the real part of s is positive, this expression will be 0 for both 0 and infinity. This integral will become this. And again, as long as the real part of s is positive, this will go to 0 for infinite time, and you are only left with this. So the Laplace transform of t is 1 over s squared. Next, the Laplace transform of an exponential. Yet again, I substitute into the definition of the Laplace transform. Here I can combine these two exponentials, which will give me this. Now, if the real part of s minus a is positive, this exponential will approach 0 as the time goes to infinity. Substituting 0 will give me this. So the Laplace transform of the exponential is this. And the integral converges as long as the real part of s minus a is positive. Next, the Laplace transform of a linear combination of two functions. This is pretty much the same as with the Fourier transform. When you crunch the integral, you will get that it is the same linear combination of the Laplace transforms of the individual functions. So when you have a linear combination like this, you can apply the Laplace transform directly to the individual functions like this. Next, the Laplace transform of a cosine. Here we can recycle the fact that we know what is the Laplace transform of an exponential. We can write the cosine as a linear combination of two exponentials, and now we compute the Laplace transform of these exponentials using this formula. The result is this. Here you can combine these two fractions, and that will give you this. The sine is pretty much the same, and its Laplace transform is this. Now the derivative. The principle is similar to what we did with the Fourier transform. You take the definition integral and evaluate it per parts. You will integrate this derivative of f, and you will differentiate this exponential. So you get this and this. Now here, for time going to infinity, as long as this s has sufficiently large positive part, this exponential will go to 0, and as long as this function f is not rising even faster than this exponential, the limit of this product will go to 0 as well. So the limit of this expression for time going to infinity will be 0. For time 0, the exponential is 1, so what I get is the value of the function at time 0. If I want to be really thorough about it, this is in fact a limit at 0 from the left. Now, what happens with this integral? I can extract this s in front of the integral, and I will get this. And this integral is actually the Laplace transform of my f of t without derivative. So the result is this. And indeed, you can see that the Laplace transform turns derivative into the multiplication by s. But this time, I suddenly have this f at 0. Well, that is how the Laplace transform deals with the initial conditions. When you have a differential equation, you can provide initial conditions to get your particular solution. With the Laplace transform, this is where the initial conditions pop up. This is actually my initial condition at time 0. Now the second derivative. The second derivative you can break into two first derivatives and deal with them one after another. So first, I use this formula to deal with this first derivative, and I get this. I multiply it by s and subtract the initial condition for this function, which is the derivative of f at time 0. Now I deal with this Laplace transform. I again multiply it by s and subtract the initial value of this function, which is the value of f at time 0. So the final formula for the second derivative is this. Next, the time shift. If you have your signal shifted in time like this is what happens. This is the definition integral. Here you can leave out this unit step and integrate only from uppercase T. Then you make this substitution, which will give you this. Here you can break this exponential into two exponentials and take this exponential in front of this integral. Finally, you get this, where this integral is just the Laplace transform of your signal x without the time shift. So the Laplace transform of a time-shifted signal x is the Laplace transform of the signal without the time shift, but multiplied by this exponential. And last, the Laplace transform of your signal multiplied by an exponential. Again, substitute into the definition integral, combine these two exponentials into this exponential, and realize that this is just the Laplace transform of your signal, except evaluated not at s, but at s minus a. So multiplying by an exponential in the time domain will cause this complex frequency shift in the Laplace domain. Okay, that was the last formula for now. The bad news is that you need to learn all of this. This is basic stuff you will need for your further engineering studies. My only suggestion is that you do not just learn this by heart, but you will keep deriving this and using this so long that it will become second nature. Now that we have gone through all the formulas, let's start using them. I will start with a simple example. Here I have this simple circuit that we used a couple of times before. This time I set my input signal to be a unit step, and my question is, what will be the output voltage when I have this initial condition? And this time I will try to find this output voltage using the Laplace transform. So this is the differential equation that describes my circuit, and I will start by taking the Laplace transform of this differential equation. Here I have a linear combination of the output voltage and its derivative. So when I apply the Laplace transform, I can apply directly to the output voltage and its derivative. When I do that, this voltage V2 will become this Laplace image uppercase V2, and this derivative will become this Laplace image uppercase V2 but multiplied by S, and the initial condition is subtracted like this. On the right hand side, the input voltage V1 will become the Laplace image uppercase V1. This initial condition is 0, so I can rewrite this equation like this, from which I can write that the Laplace image of the output voltage is the Laplace image of the input voltage multiplied by this function. If I was working with the Fourier transform and this was the spectrum of the input voltage and this was the spectrum of the output voltage, we would call this function the frequency characteristic or frequency response. When I'm using the Laplace transform, this function is called the transfer function. The transfer function is the function with which I multiply the Laplace image of the input signal to get the Laplace image of the output signal. Now to find what is the output voltage, I need to substitute for the Laplace image of the input voltage. The input voltage is the unit step, so from what we have derived here, the Laplace image will be 1 over S. The Laplace image of the input voltage will be 1 over S. When I substitute this for V1, I get this. This is the Laplace image of the output voltage. Now all I need is to take the inverse Laplace transform to get the output voltage in the time domain. But here you may start to complain that I have bored you endlessly with the formulas for the forward Laplace transform, but I did not tell you anything about the inverse Laplace transform. Well, there is a formula even for the inverse Laplace transform, but the good news is that you don't really need to use it. Typically, all you need to do is this. Your Laplace image will typically contain a rational polynomial function, and this rational polynomial you can break into partial fractions. When you do, you just go to your Laplace transform formulas and you read them backwards. So specifically, this partial fraction you can find here. So it is the Laplace transform of this exponential, the Laplace transform of this exponential when a is equal to minus 1 over RC. And this partial fraction you can find here. So it is the Laplace image of a unit step. This is a Laplace image of a unit step. So this Laplace image is in fact the Laplace transform of this exponential and this unit step, this exponential and this unit step. I can also write it like this. So this is my output voltage when my input voltage is the unit step and at time 0 this capacitor is not charged. Here I have it plotted. The blue line is the input voltage and the red line is the output voltage. You can see that when the input voltage jumps from 0 to 1 volt, this capacitor gradually charges through this resistor to that new level of the input voltage. One point I want to stress here is that in these computations we use decomposition to partial fractions, and we will use it almost in every problem. So make sure that you know how to decompose a rational polynomial function into partial fractions. Especially I strongly suggest that you learn the Heaviside cover-up method, which will allow you to do this quickly without solving systems of linear equations. Okay, so this was an example of a first order system. Now let's take a look at how we do it for a general second order system. On this slide I have an analysis of a general second order system described by an ordinary differential equation with constant coefficients. For simplicity I assume that the initial conditions are 0. Before time 0 everything is switched off and stuff happens only at time 0 and after. Now this is my differential equation, and to solve it I will apply the Laplace transform to this equation. When I do, I get this. This output y of t will become this Laplace image y of s. This derivative of the output will become this Laplace image y of s multiplied by s, and this second derivative of y of t becomes this Laplace image y of s multiplied by s squared. I repeat that the initial conditions are 0. If they were not, you would see them here too. A similar thing will happen on the right hand side of this equation, where I denote the Laplace image of the input x of t by the uppercase x of s. Now on the left hand side I can extract y of s, and on the right hand side I can extract x of s. Then I can divide by this polynomial and I get this. The Laplace image of the output signal is given as the Laplace image of the input signal times some function of s, which in the Laplace domain we call the transfer function. Here you should be careful and remember that the transfer function is defined like this only for 0 initial conditions. If my initial conditions were non-zero, I would have some additional terms on this right hand side. We will take a look at this case on the exercises. But if the initial conditions are 0, you get this simple relationship between the Laplace images of the input and output signals. And this is quite similar to the filtering in the spectral domain we had with the Fourier transform. To find the output of a system, you need to get the Laplace image of the input signal, then multiply it with the transfer function, which will get you the Laplace image of the output signal, and when you compute the inverse Laplace transform, you will get your output signal in the time domain. And how do you get the transfer function? This is how you get a transfer function. You can either do the entire derivation, or you can remember this form and just substitute the coefficients a and b from the differential equation. Now a few words about the impulse response, frequency characteristic, and stability. If I want to find the impulse response of the system, then I need to feed it the Dirac delta function, and at the output I will get the impulse response. What does this look like in the Laplace domain? The Laplace image of the Dirac delta function is 1. The output will be given as the transfer function times the Laplace image of the input signal, which is 1, so the Laplace image of the output will be the same as the transfer function. Therefore, the Laplace image of the impulse response must be the transfer function. The Laplace image of the impulse response is the transfer function. Moreover, a real-world system will not start output any non-zero values before this Dirac delta function arrives at its input at time 0. So this impulse response is 0 for negative time. Consequently, from the equivalence between the Laplace transform and the Fourier transform, if I substitute j omega for s, I will get h of j omega, which will be the Fourier transform of the impulse response, which is the frequency characteristic of this system. So when you have a transfer function and you substitute j omega for s, you get the frequency characteristic of a system. This is quite useful when I want to find out what kind of filtering my system provides. When I want to find out if this is a low pass, high pass, or whatever pass. In addition, if I know the transfer function, and I know that the transfer function is the Laplace transform of the impulse response, I can use the transfer function to judge the stability of the system. This is how I can do it. With the system described by the ordinary differential equation with constant coefficients, you will get the transfer function in the form of a rational polynomial function. In the rational polynomial function, you can factor the polynomials in the numerator and in the denominator and decompose this rational polynomial function into partial fractions. Now, before I continue, I need to introduce a bit of nomenclature. The roots of the polynomial in the numerator we call zeros because when s is equal to one of these roots, the transfer function is 0. For example, if s is equal to this sz1, the transfer function is 0. The roots of the polynomial in the denominator we call poles. The poles are the points where the transfer function goes to infinity. For example, if this s goes to sp1, or s goes to sp2, the denominator goes to 0 and this transfer function goes to infinity. Just a side note, if we were dealing with real numbers, this limit would not exist because depending whether it would be a limit from the left or from the right, we would get either plus infinity or minus infinity. But in the domain of complex numbers, where we operate, there is no such thing as plus and minus infinity. We have only one infinity and this limit exists. Okay, now that we know what zeros and poles are, we can continue. This rational polynomial function I can break into partial fractions like this. Here I assume that these poles are different from each other, which will be the usual case in this class. Now remember, this is my transfer function, so this is an alternative way how I can write the transfer function. And the transfer function is the Laplace image of my impulse response. So if I find the inverse Laplace transform of this expression, I will get the impulse response. And I can do just that. This a I can imagine as a times 1, so the inverse Laplace transform will be a times the Dirac delta function. This is the Laplace image of this exponential, and this is the Laplace image of this exponential. And this whole expression is the inverse Laplace image of this expression. So this is my impulse response. Now, for the system to be stable, I need its impulse response to be stable. I need this impulse response not to diverge to some infinity. And that will happen only if the real parts of these poles, sp1 and sp2, is negative. Remember, when you have a complex exponential, where this s has real and imaginary part, you can write that complex exponential like this, and you need this real part to be negative for this whole thing to approach 0 with increasing time. If this sigma is positive, this expression will be ever increasing in absolute value. So you need the real part of these poles sp1 and sp2 to be negative for this impulse response to be stable. So if both these poles sp1 and sp2 have negative real parts, these exponentials will asymptotically approach 0 as the time goes to infinity, and the impulse response of this system will be stable. However, if either of these poles, sp1 or sp2, has positive real part, for example, if this pole sp2 has positive real part, as the time goes to infinity, this exponential will diverge to infinity as well, and the impulse response will be unstable. Therefore, for the system to be stable, the poles of the transfer function need to have their real part negative. So when you plot the poles of the transfer function into a complex plane, and they fall into the left-hand side of the complex plane, where the real part is negative, the system will be stable. However, if only one pole falls to the right-hand side of the complex plane, the system will be unstable. If the poles fall on the imaginary axis, the system will be marginally stable. Now this looks suspiciously similar to the result that we had for the roots of the characteristic equation, and that should not be surprising. Check out what the poles really are. The poles are the roots of this polynomial, and this polynomial is essentially the same thing as the characteristic equation, except with the characteristic equation you had lambda instead of s. So you can judge the properties of your system from the poles of the transfer function the same way as you did it for the roots of the characteristic equation. In fact, this covers not only stability, but it also pertains to damping. And a side note, this complex plane where we draw the values of s, we also call the s-plane. On this slide, we will take a look at a useful trick that will allow you to quickly draw and approximate frequency characteristic when you know the transfer function of a system. On the previous slides, I showed you how you can get the transfer function from the differential equation and how you can get the frequency characteristic from the transfer function. You can take your differential equation, apply the Laplace transform with 0 initial conditions, and extract the transfer function. Then, when you substitute j omega for s, you will get the frequency characteristic. Now, you can take this expression to MATLAB and plot it, but engineers have this trick that allows them to immediately plot or just imagine an approximate shape of the frequency characteristic even without MATLAB. I will demonstrate on this example. Let our system be this circuit, which is described by this differential equation. Using the Laplace transform, I can find that this circuit has this transfer function. And as I said, I could substitute j omega for s, which would get me this frequency characteristic, which I could plot in MATLAB. Actually, I could do this for the magnitude of the transfer function, which would give me the amplitude frequency characteristic, which is what I'm interested in most of the time. Now, what if I want to be able to draw this without MATLAB? To do this, I first need to be able to imagine what this magnitude of the transfer function is. This magnitude of the transfer function is actually a real valued function of a complex variable. So essentially, its plot is going to be a surface over the complex plane that is over the S-plane. Here I have the complex plane, the S-plane. This is the real part of S, and this is the imaginary part of S. On the vertical axis, I draw the magnitude of h of s, so this surface is the magnitude of the transfer function drawn for various values of s. Now, this plot of magnitude of h of s has two important features that are related to zeros and poles of the transfer function. Observe that this transfer function has a zero at the point where s is equal to 0. That means that when I substitute 0 for s, this transfer function is going to be 0. Also, when I substitute 0 for this s, the magnitude of the transfer function is going to be 0. You can nicely observe that here. Note that this is the point where the real part of s is equal to 0 and the imaginary part of s is equal to 0. So this is the point where s is equal to 0. And at this point, the transfer function is also 0 because it has a 0 at this point. Next, this transfer function has a pole at s is equal to -1. Observe that when I take the limit of this transfer function with s going to -1, the transfer function will go to infinity. And also for the magnitude, when I take this s to -1, this magnitude will go to infinity. And you can see that here as well. This is the point where the real part of s is -1 and imaginary part of s is 0. So this is the point where s is equal to -1. And over this point, the magnitude of the transfer function goes to infinity. So the position of zeros and poles affect the shape of the magnitude of the transfer function. Where there is a 0, you will have this valley, and where there is a pole, you will have this infinitely tall hill. So when you know where the zeros and poles are, you can get an approximate idea what the magnitude of the transfer function looks like. Typically, we do not draw these 3D images, we just imagine them in our heads. If you ever need to indicate this shape, you draw it like this. This is essentially a top view on this plot. This is a complex plane. This cross indicates that there is a pole at s is equal to -1, and this black circle indicates that there is a 0 at s is equal to 0. These contours indicate the shape of the transfer function. These blue ones indicate the presence of a valley created by this 0. And these red ones indicate the presence of a hill created by this pole. From this plot, I can approximately imagine that there is a valley around this 0 and that there is a hill around this pole. Okay, now that I have finally realized what is the shape of the magnitude of the transfer function, how can I use it to get my amplitude frequency characteristic? To do that, I need to realize what this substitution means. When I substitute j omega for s, that means that I limit my complex frequency s to the imaginary axis only. And the values on the imaginary axis are my angular frequencies omega. So for example, if my angular frequency omega is 1, my s will be 1j, which is this point in the complex plane. And when my angular frequency is running from minus infinity to plus infinity, it goes through the s-plane like this. Like this. So when I say that my amplitude frequency characteristic is the magnitude of the transfer function at s is equal to j omega, that means that my amplitude frequency characteristic are the values of the magnitude transfer function above this imaginary axis. These values. In this figure, I have removed the plot of the transfer function magnitude for the right-hand side of the complex plane so that you can see it better. This is the imaginary axis where s is equal to j omega, and these are the values of the magnitude of the transfer function for s is equal to j omega. So this is my amplitude frequency characteristic. You can see that it corresponds to the frequency characteristic I have drawn in MATLAB. Again, typically you are not going to draw this 3D plot, but you work with this sketch in the s-plane. And here you can see it too. When I substitute j omega for s, that means that I limit myself to the imaginary axis, and the values on the imaginary axis are my angular frequencies omega. And the amplitude frequency characteristic will be the values of the magnitude of the transfer function above this imaginary axis. So when I start from negative frequencies, following these contours, I can see that as I increase the frequency, I go down the valley, all the way to 0. And that is what I can draw. I go down the valley, all the way to 0. Now when I continue increasing the frequency, I go from this 0 up the valley, and that is what I can draw. I go up the valley and up the valley. So by tracing the values of the magnitude of the transfer function about the imaginary axis, I can approximately draw the amplitude frequency characteristic of my system. Of course, when you draw your frequency characteristic like this, it is going to be very approximate, but qualitatively this approach is sufficient to recognize that this system is actually a high-pass filter. This 0 in the origin will cause this dip in the frequency characteristic, so the lower frequencies will be suppressed more than the higher ones. Now, when you design a control system or a filter, during the design process you often move the positions of these poles and zeros. And it will be expected of you that you can quickly imagine what kind of frequency response different distribution of poles and zeros gives you. So you need to learn this and be able to quickly do it from the top of your head.